succeed if I find that these two proportional states, and if you can define this field. Sorry.
Is that fine? Which way? Like shift it this way? Oh, turn it. Yeah.
I mean,
and what's the time? Is it time to start? Well, 1 more minute. So let's give it a minute. Can you check that your markers are working?
See, I missed that. Try not to say maybe a bit of
We can start. So for those who just came in, we'll have a group photo right after this talk before lunch in front. Hopefully rain will not fall in the meantime. We're very happy to have Anton Kapustin give us a talk about anomalies, bulk boundary, correspondence, symmetries, something like that.
So I'm very happy to talk at this very stimulating conference. Sorry for being 1 day late. I was delayed, not because of my fault. So I'm also excited to give a talk using whiteboard, and I'm also a bit scared because whiteboards are whiteboards in general tricky. So
We should put the microphone. Sorry, I forgot.
sorry, after, yeah, no.
Oh, you have it.
I have it just
On the top.
Yeah, yeah. Okay. Now it's green. Yeah, so I once visited Israel for 3 months. They put me in an office with a whiteboard, and the marker turned out to be a permanent marker. They covered the board with some formulas, and then that was it. For the next 3 months, I didn't have a whiteboard. So I don't know the doctor I left. Anyway, so the focus doesn't have to here. So I'm going to talk about some. Well, I want to motivate. This is a QFT conference, path to QFT conference. I want to motivate. I'm going to talk about from the point of view of QFT. I think one problem that not enough. Well, I want to advocate more people should be working on defining QFT in a mathematically rigorous way. And physicists have this attitude that the rigor is not terribly important. But I think sometimes it is important, especially in those areas where you don't have much experiment to help you. So, and monofield theory is, I think, one of those problems where it would be nice to have a rigorous definition. And actually, people tried say the result is not very inspiring. So the kind of axiomatic definition, well, there's several attempts to like axiomatic definition of quantum field theory. I guess historically the first one is Whiteman axioms, well, but nobody takes them seriously anymore. So that's a very weak set of axioms, which doesn't even require conserved stress under tensor to exist, which is pretty important.
They're not taken seriously because they're too weak. They're not.
Yeah, they're very weak. They're very weak. Well, yeah, we believe that they satisfy any quantum field theory, but they don't tell nearly enough. And there are some pathological, from a normal point of view, examples which don't really regard as valid quantum field theories, like say general free field. So which is not something considered quantum field theory. They're not able to define what it means for it to put it on a curved space or anything like that. Because it doesn't have stress under tensor, but allowed with its axioms. Now, so basically, yeah, so all the axioms we have are either general enough or don't incorporate, well, not something which is general enough, but also incorporates all non-constraints. I'm not really sure what those are. So, topological field theory seems a bit better. In topological quantum field theory, there are some sort of axioms, everybody probably heard about Siegel's axioms, which proposed Matthias Siegel axioms proposed back in the 80s. Well, that turned out to be, well, those axioms are reasonable, but they're not, don't incorporate all constraints. So, now, well, probably many people heard that there is an improvement on those. So it's something, well, what's wrong with this axiom is that they don't incorporate locality sufficiently. So, for example, in these axioms, you have to take a, say, manifold, closed, say, D manifold, so D is space dimension. And attach to it a vector space. But there are lots of manifolds, well, except if it equals 1, there are lots of closed manifolds, and what is the relation between different vector spaces? Well, to answer that, you would need to say what happens if you, how to compare the spectral space. You need probably to say, well, we can make these manifolds out of more basic building blocks, so you can cut them, and then, but then once you cut them, the boundary is a D-1 dimensional manifold. It can still be complicated. You need to cut those two. Probably heard that there is some attempt at defining, within topological field theory, define the structure, and then, but then well, the result is not something that the physicist can understand easily, or even mathematician. So you get something called, really say, well, you need to think about some D category or something like that, or D infinity category, or infinity D category. So I have yet to meet a person who actually understands what an infinity D category is for general D. That's not people who know what infinity 1 category is, but that's good enough for like one-dimensional quantum field theory, but well, one spatial dimension. That's not very interesting. Well, it is interesting, but not enough. So, so even topological field theory is complicated. So, and I think part of the main problems in quantum field theory are remain unsolved, like the famous Young problem, in part because it doesn't know what quantum field theory is. So now I would like to advocate that perhaps we can learn a little bit more by studying lattice systems. Wonderful lattice system. So let's see. I'll actually erase it. So now, so why? What's the connection? Well, first of all, quantum lattice systems. Well, there are two issues when defining quantum field theory. You have to deal with U divergences, but you also have to deal with infrared issues. And at least lattice systems allow you to deal with infrared issues. So maybe learn how to deal with those, and then move on fixing the UV issues. But that's kind of very yes.
I'm a little bit confused. Normally, I think about lattices as something with UV issues, not IR issues.
So what?
Normally, lattices regulate UV divergences, not IR.
Yeah. So I'm saying.
Oh, sorry.
I'm saying that in quantum field theory, the subtlety involves because of UV divergences and some IR issues. And lattice systems that deal with the, they don't have UV issues, yes.
Good.
Yeah, so we're saying that, but then you learn how to at least work, how to take into account these IR issues. But there's actually more concrete reason to be interested because it's like, you would think, okay, so maybe you solve IR issues, but you still have UV to do with. More concretely, there's one reason. Well, first of all, gap lattice systems with an energy gap, is somehow very roughly related to topological quantum field theory. So now this is actually, well, I put roughly because of course there are examples now of gap lattice systems which do not seem to be described by topological quantum field theory, namely fractons. These are very nice lattice systems, but nevertheless they have the weird infrared properties. Well, we can get rid of those by a simple trick by looking at on short range entangled. Systems. So those supposed to correspond to invertible. It's called invertible PTQFT. Well, it's not nobody knows if every short range entangled gap system, well, actually short range entangled implies gap. So what does short range entangled means? Well, it means that you start with you can prepare you can prepare your system together with some unentangled ancillary degrees of freedom, starting with a trivial state. You start with an unentangled state, and you're able to prepare the state of your system in infinite volume by evolving this unentangled degrees of freedom. You produce that plus some other junk you don't care about, which is not entangled with what you care about. That's what the range entangled means. And it's believed that there is some way to attach in the topological quantum field theory to such a gap lattice system. There's no proof. There's just lots of evidence that's the case. But also there's some difficulties. For example, in invertible topological quantum field theory, you have well, if you look at case equals 2, so three-dimensional topological field theory, then we know that there's a quantity there known as the chiral central charge, which we know exists here, but we don't know a way to assign this number called chiral central charge to a short range entangled system. So, so it's non-trivial even in this case.
Why does that eliminate fracton phases, short range entangled?
Well, any short range entangled state has a non-degenerate ground state on a torus, for example. So
that eliminates.
So that eliminates all counterexamples. Doesn't mean it eliminates all counterexamples. It eliminates only those we know about. So as far as I'm concerned, this relation is completely conjectural. And actually, if it were true, it would be amazing, because well, this is something you can define for any spatial space-time manifold, right? And well, the TQFT. But for short entangled systems, there's not. What's the connection? You start with some lattice in d-dimensional space. What's the connection with the manifolds in d+1 dimension? None. So that would be amazing if it were true, actually. Anyway, so another reason. Yes.
Yeah. How to tell whether a lattice system is short range entangled or not?
Well, I mean, but by definition, well, you didn't draw this definition. So you start with some state of a system. So here, this system can mean different things, but one could just say system is just a state of a lattice degree of freedom without the Hamiltonian as a state, which happens to be a ground state of some Hamiltonian, but you don't really care which one. So you start with some state. So you start with some unentangled state. In infinite volume. And you say that you evolve it with some unitary circuit. And you get your state of interest plus some junk which is not entangled, so just a tensor product of the state. So if you manage to do that, then you say the psi was shortly entangled.
Is this actually like really possible to do in practice? If I hand you a random Euclidean lattice field theory, can you tell if it's gapped, like realistically, or
So
is it entangled? It's a hard problem.
So what's I don't know Euclidean.
Well, if I hand you the action for Yang-Mills theory, can you tell that it's gapped? I mean,
Of course not. That's
yeah,
the whole
exactly.
point.
But then
First of all, I would say that first of all, action is kind of not relevant data in any case.
okay.
I would say QFT in a good shape if we're looking at a model which have actual semi-classical limit, like say Yang-Mills theory is a freedom. But if you look at non-random monofield theory, nobody even knows what that is. So that's mostly a question about how to deal with non-random field theories. And as I say, Yang-Mills case is better than most. Actually, is no definition short distances. Of course, there's a different issue there, right? Namely, you still need to explain like what it means to construct Yang-Mills flow distances, right? So I don't know what this means because, but we know enough construct that if somebody constructs something, some set of correlators, they lots of constraints, and you could also show that they agree with short distance, expect short distance behavior, you would say, well, you solved the Yang-Mills problem, right? But the problem is we never know what all the constraints we need to check. Nobody knows what the constraints are. So, yes?
So I just wanted to make sure I understand something. So it seems like you're using a slightly different definition of short range entangled from, I don't know, one that's commonly used where we, in the sense that you're allowing this other junk. That's fine, but I just want to make sure.
Right.
Is the reason why you're using that because you want like a chiral state, like the E8 state to be short range entangled?
No, I think the reason, well, okay, so maybe I shouldn't call it short range entangled. Invertible.
And just to make sure, you wanted to include, so you want us to claim that E8 state satisfies this definition, I suppose, right?
Yeah.
Do we actually know that?
No, we don't. We don't know what the E8 state is to begin with. So like, yeah, so.
Okay, fine, sorry.
Hopefully that's the right definition. And one measure of the question, whether it's a right definition, is can we reproduce the E8 state? If there's something we should call the E8 state which can obtain like this. Maybe there's no way to get it like this. That's the wrong definition, presumably.
I didn't quite get what the conjecture is. So is it that I take one of these, I take invertible lattice systems and I take the infrared limit and that gives a surge action to invertible TQFTs or bijection?
By system, right? So if you define a system this way, so then this state is just a state and there's no Hamiltonian, but there's some, by construction, there's some Hamiltonian, for which it is a gapped ground state. So there's no IR limit, or it's already the IR limit because I discard everything except the ground state. So the conjecture is that if you take the set of all such guys, which can be obtained from an entangled state by some circuit, and you identify, look at the equivalence class of such states under some suitable equivalence relation. For example, we could say, well, if you can convert one such guy to another such guy by circuit, then certainly they're equivalent. You can modify that. So you define several equivalence states, and you can also define several, isomorphism classes of this place. There should be a one-to-one correspondence.
Okay, bijection.
Yeah, but how it's exactly arranged, we don't know, but that's a good. Just say that for here, we can actually write down this set specifically. That's because even though we don't know what TQFT is, there is by now a reasonable definition of invertible TQFT. special case. One good thing is you don't need to know what infinity D category is. You just need to know what infinity 0 category is somehow. So that's easy enough, so you can actually make sense of this without some, well, infinity 0 is also pretty complicated, but better than infinity D. So you can make sense of that, and actually can classify that, and that's not trivial result. And you actually, in every dimension, I can write down, well, at least the number of non-invertible PTQFTs after isomorphism. That's a computable thing, and we would like to believe that that's also what you get from lattice systems.
But still, the conjecture doesn't. It's not clear what you would check because invertible PTQFT is a huge amount of data. It's partition functions on manifolds. That's the data.
Yeah, well, I mean, yes.
Yeah, what does this even mean to say that they're the same? You don't have this data on the left-hand side.
Oh, that, of course, if you just say that two sets with some unknown bijection.
Yeah, you're saying that there is an unknown bijection.
But still, if you manage to, for example,
every two
to show that the numbers, that even the number, for a set without any structure, you just have a number of elements in the set. But still, let's say, in this dimension, there are 17 invertible topological classes of systems. That would be pretty cool. But of course, there's more information than just bijection of sets. Well, there's a more detailed conjecture called the type conjecture, which can explain what exactly is supposed to be the same, not just set projection of sets. Now, another problem, which is also relates lattice system and QFT more directly, is anomalies. So roughly speaking, what you have, say, T plus one dimensional quantum theory, which happens to be topological and invertible. Then on the boundary, well, one signature of the fact that it's non-trivial one is on the boundary of this. If you actually put a physical boundary, some say half plane, then you've got to have some gapless degrees of freedom there. And if you believe, well, if they describe a quantum theory, which is not at all obvious, then those degrees of freedom have to have anomaly. Well, if it's a symmetry preserving boundary, then that symmetry preserving boundary must have a tooth anomaly. And what is a tooth anomaly? Well, it means that there's an obstruction to gauge it. Obstruction.
Is this relativistic QFTs or any QFTs?
Well, that's the question, yeah. So, of course, in general, we don't expect that for particular choice of Hamiltonian that the boundary is going to, and the boundary is going to have relativistic quantum field theory. So, presumably, there is some very general definition of quantum field theory which is not relativistic, for which you can make sense of the statement.
But was there a classification like Fried-Hopkins for manifolds with a Cartan structure or Newton's some smaller structure?
Well, first of all, when I say it's conjecture, one of the reasons it's a conjecture that Fried-Hopkins itself depends. What do you mean by QFT means? It depends on what sort of what do you mean by manifold, right?
Yeah.
So,
which structure?
Many choices, right? Now, that's without symmetry. But once you decide what to do without symmetry, you can say, well, you can also add in symmetry by saying, well, there's some G bundle here.
No, but even without symmetry, they assume diffeomorphism.
Yeah, so that's not clear at all. Right? That's true.
Maybe you want to only assume Cartan structure or something like that. Some Cartan structure.
What's Cartan structure? Oh, but
like a foliation.
Cartan, yeah, maybe. Yeah, maybe. So it's not the way. So anyway, so there is some relation between QFT and absolute anomalies, and I would just let's say, okay, why do we care? Because understand these issues anyway without PTQFT? Well, I would say we have some understanding, but it's not very satisfactory. One thing which is not clear to me, well, I think understanding better with anomalies is actually would help understand the symmetries in general in quantum field theory. So, and one thing which I regard as unsatisfactory is that I don't really have a good understanding of robustness of Swift anomalies because usually it's well, what's the abstraction to gauging? Well, gauging itself is not easy to define, especially like in non-Lagrangian quantum field theory. And I would like to have a definition purely in terms of global symmetries. If somebody hands me say correlators in the field theory, or maybe an operator algebra in some action of a symmetry group, I'd like to be able to decide whether there is an anomaly or there isn't an anomaly. And in some cases, we sort of know how it's done, but not in general dimensions. So, and I think, well, if you assume that this invertible is the same as kind of like invertible lattice systems, then you can try to see you can try to understand what happens, what's weird about global symmetries in this quantum field theory on the boundary by studying what happens with the global symmetries with the bulk lattice system. So let me explain what I mean in more detail. So here. So in D equals, well, the good case is D equals 1. The case which we understand best is the case of one-dimensional quantum field theory, one spatial dimension. So in that case, we have so I have some charge, and let's say G equals to 1. So some charge is an integral with charge density, and so Q is a symmetry in the sense that it comes with a Hamiltonian, and also preserves the ground state. Now, how do I see that as an anomaly? Well, first I write my Q as an integral of some local quantity. Then I define some smear charge density and ask, okay, what happens with whether it's true that the commutator of the charge densities can be made vanish. So if you want symmetries, you would expect that the smeared charge is actually all element abelian. And well, it turns out that in general, it doesn't work. You get that. That the commutator is not a 0, but some central term like this. So that's called a Schwinger term. Well, I can make it into something more familiar if you fully expand this. Well, you imagine the x is x in a circle. You can just take a Fourier series for f, and then just smear with a particular.
Sorry, what is G here?
Two functions. They have two functions. So if you take like e to the I in theta and g e to the I in theta, where theta, well, x, yes. Then you get some statement about Fourier modes of this density in a circle.
So is it two smearings? One is smeared with F, one is with G?
Yes.
Is that, okay, I can't see where.
Yeah, so yes, we can just say in terms of Fourier modes. So there's some central term in the commutator of the Fourier modes. We also maybe do this way you can do it like on a line. So the Schwinger term is significant. It's actually an anomaly. And the good thing about this is somehow operator algebraic statement. It's not about statement about correlators. It's about the level of operators. So I would like to something similar in higher dimension. Yes.
Sorry, what is K here?
Some number called that measures anomaly.
Oh, okay.
So
Also, this term only appear when there is anomaly.
yes. So if it's there, you have an anomaly. If it's not there, you don't have an anomaly. And so you have a classification of different anomalies by the integer.
So any anomaly must be of S partial T form.
Yes. Any anomaly must go this form. Bill proportion turned on.
Okay.
Yeah. So I'd like to have a similar understanding of anomalies in higher dimensions, for example. And there, okay, we think we understand anomalies very well in higher dimensions, at least, but really we understand them mostly, again, for theories like the free fermions or the couple theories. And moreover, I don't think we have a good understanding of how to do something similar for anomalies in higher dimensions. Namely, usually it's stated as something about correlators of current, not about the operator level. And there are some serious difficulties with operator level statements like that.
This also does not capture global anomalies. This is some kind of a
Yeah, I'm trying to just looking at simplest. Yeah, but let's talk about anomalies. So this is first of all a deviant, but it actually doesn't matter too much. Second, of course, it's it's a Lie group symmetry, and I just care about infinitesimal anomalies here.
Yeah.
But even within this setup, some other class anomalies are a bit more complicated. Say gradation anomalies are much more complicated because well, that actually goes back to this issue. When you have a so some particular PTQFTs correspond to purely gravitational anomalies on the edge. But it's really surprising to have a notion of gravitational anomaly for a theory which actually doesn't have any Lorentzian variables. So what is that? So well, to me it suggests that whenever gravitational, there is a way to rephrase gravitational anomaly without making a reference to stress energy tensors. But how to do that? Great. So, but at least I'm going to focus on global symmetry because I don't know how to deal with this other anomalies.
But even global symmetries can have sub-non-perturbative anomalies.
Yeah,
and even
I'm not touching those either. Yes, so for d equals 1, actually, there's a problem even saying anything like that. And what's the problem?
So isn't it logically possible that all nice sort of short?
Sorry?
Isn't one logical possibility that all nice short entangled or vertical phases just have zero chiral central charge? Some people have tried to argue that in some contexts.
Well, since you don't know, yeah.
No, I know.
Okay, so
you're hoping that that's not the case.
So there are free-Fermat systems, right? So which have certainly there are free-Fermat systems which have a non-zero chiral central charge, the chiral ones, right?
Got it.
Right. Any Chern insulator has a non-zero chiral central charge. I don't know.
But you're restricting to a special class of gap system.
Yes, it's a big question. Whether we can certainly define chiral central charge for free-Fermat systems. Sure, it's just equal to their Holton lattice, whatever works. You can define it for those. It's an open question whether it can be defined for general lattice systems. Maybe it can. I don't know. Maybe it's just not well defined. They don't prove that this corresponds to TQFTs, invertible TQFTs and invertible lattices just wrong. They certainly have invertible TQFTs with non-zero chiral central charge.
So in the D-equal-1 example, where did you use that this was a symmetry? That I mean, you wrote that Q commutes with H, but
point that takes another symmetry. So the only trade with. So our rho at F is a generator some transformation which actually don't commute with the Hamiltonians. Only for constant F do we have commutation.
yeah, but where did you use that for constant F? I mean, in what you wrote.
If you just try to ask what can happen here, right? Certainly F or G are constant.
Okay.
You have zero. Now, because it leaves plenty of opportunities to have lots of expressions like that, right? Okay, this is a constraint from Jacobi identity, but for a billion Lie algebras, like here, the only constraint is symmetric in F and G. So you just try to write down something on the right-hand side. The only constraint you have is that it's symmetric in F and G, and then the advantage is when F or G are constant. Lots of expressions like that. You can put any odd number of derivatives here, and that's valid. So, and that's not trivial. But for some reason, you only have that. I don't know why. So, now of course, what you can get here itself depends on what this means. And actually, there's a lot of ambiguity in how you choose this, given that. You can add total derivative, not going to change Q. So the claim is that somehow anomaly means that no matter how you define rho for a given Q, you're always going to get this problem. And moreover, this K is going to be dependent on how you chose your rho. So somehow, despite all the ambiguity, there's some invariant information there. Now, in higher dimension, what's the problem? The problem is that there's no such thing as a rho of F. So, and that's true whether there is an anomaly or there is no anomaly, just not there. So, let us explain in this paper by Rajiv. So, the paper, well, the argument itself, well, the paper is mostly not about that, but section 2 proves that. The proof, unfortunately, is wrong, but if you would exercise to go and find the error, the conclusion is still correct. So what we proved is that if you start with free fermions, first, if you start with, say, the simplest example of field theory, free fermions, and ask whether this is well definable, the answer is there's no, it's not well defined operator for nice smooth function F.
Is there an intuition? Why not? I mean, it doesn't seem intuitive that you can't define it in the same way.
Well, in theory, it's not clear they're well defined either. We can normal order with respect to vacuums for free fermions, and you get a well defined operator. If you try to do the same thing there, it doesn't work. Normal ordering still gives you a well defined operator.
Is it a problem of smearing? Because in axiomatic field theory, you're supposed to smear about space-time in both directions. In your left-hand side, in 2D, it's considered to be okay to smear just over space.
Yeah, I don't think it helps though. It's even to smear in space-time. Yeah, so they do it in space. Yeah, maybe that's a issue. But
Is there any, sorry, is there an example of what happens?
What exactly is well defined or not well defined?
well, just compute this thing. What is the norm of this?
No, but this has infinite frequency modes. Of course, it's still defined. You have to remove the infinite frequency modes.
Well, here's things here, but I mean, the point is that F itself can be chosen by very smooth, which means its Fourier components decay very fast.
But it has infinite frequency support. Of course, it's divergent.
What enough force? In one dimension, it's not.
Yeah, I know why it happens in 1D, but in higher D, it's known that you have to remove the infinite frequency modes. It's a trivial statement.
Okay, so we take the usual definition of charge density, and they smear it, and they say that you get this problem.
No, they smear it incorrectly. Usually you have to go a little bit to Euclidean time or smear in the time direction. If you do that, you have infinite frequency support.
Well, I can try to do that.
And then everything is well defined. It's if you smear in the time direction.
Maybe, but the question is, what is the manifestation of anomaly there? So it's not like that.
Right.
And I don't think it's known what the exact statement is because, no, it's not known on operator level. Well, what I like right now.
There is a similar C number in the. I mean, there is if you do the commutator of two densities which are appropriately smeared, you get another density. It's a JJJ structure constant.
No, but the question is, okay, so you do get another thing. The question is, what's the statement about anomaly? Because this rho F itself is ambiguous. Maybe there's something to define it, but then how do you expect anomaly out of this algebra which involves
It's in the 3-point function.
Sorry?
It's in the 3-point function.
I don't want to use 3-point functions.
Oh, you don't allow, okay.
So you want to do operator statement because I want to explain why anomalies are robust. The ground state depends on coupling to the Hamiltonian or whatever. So I want to say that operator algebra.
because you want to go to the lattice at the end of the day.
Because I want to say, well, robustness, well, anomalies explained by the fact that there's some symmetries act in a weird way, in some strange way on the algebra observables. And then it doesn't matter how I sandwich them in which state, I always get the same result because there's some operators take level statement. So in my opinion, operator level statements will explain why anomalies are. Well, we don't really have an understanding of why they are.
Well, to be honest, anomalies are defined in QFT modulo Q-exact terms, what people call Q-exact in the descent. And if you give a Lorentz invariance, I don't know if there are anomalies. I've never seen a classification.
Well,
so it might not be.
If you think about boundary correspondence, you would say that, say, if you have a bulk which has a non-trivial phase, an invertible phase, then the boundary might have anomaly, whether the edge is in a Lorentz invariant sort of situation or not. Say performance, like, oh, everybody would say, okay, yeah. That's gonna I'd like to talk later about how to see that there is some. Wait, here's a statement. If you go back to like lattice systems, you would say the following. Suppose you have a lattice system where in the bulk you have non-trivial lattice system, and on the boundary, therefore, expect to have a system of anomaly. What does it mean? What statement about charge densities you can write down which makes sense without an positive invariance? And in one, so in one dimension, that's sort of conjectural, so that you can see this whenever the bulk is in a non-trivial phase, you're going to have this on the boundary. So I'd like to actually make it more precise in this talk.
What about the suggestion of Fadeev and Shatashvili, which is that the wave function is a two cycle?
I should mention, like, these people, by the way, they made some, the bulk of the paper is not about this issue, but how to go around this issue. And the way to go around this issue is to, well, which is also actually present in the early work of Fadeev and Shatashvili, is to say, well, you're not going to work in the original Hilbert space. You're going to consider all field theories which couple a gauge field. So you have a family now of field theories parameterized by the possible choices of the gauge field. And then, say for d equals 3, so let's say use so introduce gauge field. And now everything depends on the choice of this gauge field. And now it claims that if you do that, then you can make sense of sort of enlarge your Hilbert space for this gauge field. Let's say that I don't know the coefficients, but something like this. Here's form notation. So that's a 1 form, it's a 2 form, so integrate over the whole space. And A is the background gauge field. And now I can say, well, what about A itself? How does it commute with the this row? Well, and of course, A is commutes with like this.
A is not a background, it's an operator now.
Well, no, here in their description, just a background, classical background. But you want to look at the algebra. So this row in their description doesn't just move inside Hilbert space. It moves also in the parameter space. It's like a differential operator. Like you have a family of Hilbert spaces, and it moves you on the parameter space as well as in Hilbert space. So it includes a vector field on the parameter space. So in that sense, A is some function of the parameter space, a coordinate function. This is how the vector field acts on this function. The way it acts as you would expect by gauge transformations.
Okay. So why does rho have to? I mean, this is just the 3 + 1 caret non-different. Why can't rho just be the current density, charge density?
Why can't rho be what?
Why does rho have to act on? You said rho changes the Hilbert space. I mean, this is just the 3 + 1d.
Well, the point is within Hilbert space, they weren't able to make sense of this rho of f. But in the sake of make sense of it, they think about like a family of Hilbert spaces of free field theories over parameter space, which is the space of all gauge fields in 3-dimensional space. So, and then if you interpret it in that way, you can make sense of it. And then rho of f is a so you have a bundle of Hilbert spaces, say 1 Fock spaces or whatever. And then the algebra of these rows, which is now a vector field on the base, which is now some differential operator on this section of this line bundle, obeys this. So
So you didn't write down the definition of rho.
Yeah, I didn't. I'm gonna do that.
Okay, so you're
It's
just
not
saying
great.
it has this property.
Yeah, I want to display this because somebody's going to come up with lattice system. So that's, by the way, essentially what's called the Faddeev-Shashvili algebra. So and the anomaly is basically here. Yeah. This case anomaly.
But you can also just derive this equation from the 4D chiral anomaly.
Yes.
And there,
Clearly just a 3-point function.
yeah. So, yeah. But there you don't need to interpret rho as some funny thing. It's really just the density.
Yeah.
If you derive this from the 4D chiral anomaly, rho is just the charge density. It seems like a simpler interpretation.
Well, it is charge density. The
Yeah.
point is simply you cannot interpret the charge density as an operator in fixed Hilbert space.
Okay.
So, but if you allow it to move you between different Hilbert spaces, then you need to include then you get a cycle, but it depends on where you are on the base. A cycle, well, it's a trigger term which is itself a function something. Rather different from what you have in one. Okay, so I'd like to, well, I'd like to see something like this or this from the bulk point of view. And by bulk, I mean some lattice system. And in particular, I would like to make it plausible that any degrees of freedom on the boundary must have some weird realization symmetry like this. And moreover, I would like to see that in some sense, higher symmetries actually make an appearance. So that's one other thing which is unsatisfactory about most definitions of quantum field theory is that, well, sort of the popular perspective nowadays is that symmetry in d dimensions is not just a group. It's a d plus 1 group of d spatial dimension. So now, the usual definitions of quantum field theory are making a reference to dimensions. They don't move the same in all dimensions. So a good definition would actually make it clear why there are different, why symmetry means different things in different dimensions. So I'd like to argue that actually once you try to understand this issue, you also end up with some higher symmetries.
So what happened for the equal to 2 case? Why did you jump from 1 to
Sorry?
3? What happened to the equal to 2? Can you define like a Faddeev-Shashvili operator?
I can't hear.
Why did you skip the
Why you
equal
skip
to 2? That's the question.
Why is it equals to? Well, because
If you're studying perturbative anomalies.
well, in there are no anomalies supposedly, but it's a good question. What? Yeah, so I'll come back to that maybe. So we'll discuss that. Well, usually people say that there you don't need to have this term, just get 0 inside and yeah, live the cycles. Okay, so my goal is to see how this weird algebras arise from the bulk, where the bulk is some gap lattice system. So I want to talk about first of all, what I mean by gap lattice system. Well, one big difference compared to, well, why equal working in infinite was important is that the whole starting point is different in ordinary quantum mechanics. And in quantum mechanics, you usually start with Hilbert space and say observables are bounded operators in the Hilbert space, or self-adjoint bounded operators. And then the symmetries are just basically whole unit. Well, you also have time evolution, which is given again generally by some Hamiltonian, and then you say, well, symmetry is any unitary which commutes with the Hamiltonian. So now, in higher dimensions, you're supposed to do something different, because you would like to see that symmetry is not simply a group, it's something like D group, D plus 1 group. So, in QFT, well, I'm not going to discuss QFT, but in lattice systems, already you see that why it should be a difference. First of all, you don't have a Hilbert space from the outset. You have algebra observables, with local observables. And given the dimensions, just take a large tensor product, infinite tensor product of matrix algebras, because I assume that in every site we have just a finite dimensional matrix algebra. Each of these guys. Algebra matrices. Well, and then to get something called C star algebra, you need to sort of take closure. So you need to, well, only, this, if you just don't, take closure means to get some object which has a nicer analytic properties, namely, it's complete in the sense that any Cauchy sequence in this guy actually has a limit. So without that property, you can't really do analysis. Anyway, so this is multiple observables, and they don't have Hilbert space, it's some abstract algebra. And at this level, there's no dimension yet of space-time, because it turns out that if you take, say, suppose you always AJ are 2 by 2 matrices, then it doesn't matter what the dimension is. All these algebras are abstract, they're isomorphic. So now if you ask, for example,
so question? You take the tensor product of like larger and larger regions, or?
Yeah. So if you don't complete it, so what does the element of this looks like? It just means that it's an infinite number of ones and a finite number of non-ones. Okay. That's why tensor product of algebras makes sense, but taking tensor of Hilbert space doesn't not very useful, because in a matrix algebra there's a special element 1, but in the Hilbert space it's a special vector. So yeah, taking tensor product of algebras actually is a sensible procedure, and gives you something which is quasi-local. An element of, if you don't close, and an element of this is what's called local observable. It comes with everything outside some ball. But if closure is called quasi-local, some tails. Anyway, so then how to get to operators? This is just some abstract algebra. Well, to get to operators, well, first of all, turns out that here you don't have Hilbert space, and you don't have operators in Hilbert space, but you can still define notion of evolution. So an evolution now is a unitary operator. It's what's called automorphism, which depends on the parameters. We have some map like this. And you have a condition. It also has some nice properties. It's called one parameter group of automorphisms. And you say, well, first to define a system, I specify this and specify that. And then this is my setup, and I have to solve for it. Solve for what? Well, so solve, for example, for the ground state.
Wait, what about locally generated?
Sorry?
What about Hamiltonian being local?
Well, yeah, so at this level, again, you won't see anything different in different dimensions. For example, a symmetry of this thing is defined the same in regards of dimensions. So which can use some automorphism which can use with the automorphism. But of course, in reality, you only deal with very special time evolutions coming from local observable. Sometimes close with the local evolution. So, and but first of all, let's explain. Yeah, so, what does it mean to solve the system? Well, you're looking for ground state of this evolution. What does it mean? Well, first you define sort of Hamiltonian, which will generate this evolution. But now again, it's not operating in any Hilbert space because there's no Hilbert space yet. So. So, well, you define, it's called H as a map from algebra to itself. And the way you can extract it from time evolution simply by saying that H, let's say, observable, is so, and
What do you say now?
inobservable.
And when you say algebra, the algebra is the algebra of these observables.
Yeah, this one. So now I'm a little quote, but it rather turns out this derivative doesn't exist for all observables. So there's some nice observables which exist, but in general, put an observable that's not gonna really define. This function just doesn't have to be differentiable for general observable. Well, that's a bit of a difficulty. I'll deal with it later. The point is that so H, so such an object has a property that check. So H is a derivation, and actually that's true about every single symmetry, not just time translational symmetry. So every symmetry from the point of view, well, symmetry from the point of view of this abstract approach is just a derivation of the algebra. It's not an operator.
A derivation means the formula 2 lines above.
Yeah, that's what it means. This one. This derivation. So Leibniz rule is defining law.
It means it's a derivative. That's what derivation means.
Derivation means it satisfies Leibniz rule when acting on the spectrum space.
I'm not sure this is a meaningful question, but is it possible to get an example of some of this for some simple lattice model, like a scalar?
No, sure.
What does it look like?
I'm not doing scalars, I'm doing spin systems. So each of these
Spin
guys.
chain.
Spin chain.
Yeah.
Okay.
Now, in practice, of course, nobody ever gives you this. Right? You usually give yourself H and then try to sort of exponentiate it and get alpha. So how do we sensible H's and describe explicitly without knowing time evolution? So typically, H of A is given by a formula like this. Where each AJ is itself observable, localized on some site J, like living on some site J. So the point is that if I just had an individual term here, it's just a commutator with an observable. But the infinite sum is not a commutator with observable. Okay, so that's why it was a difference. Infinite sums, so H is, there's no observable you could call H, because it's derivation you call H. Yes?
So, did you impose any information from the lattice system with the gap? Or
Not yet.
not? Okay.
Yeah, so now usually the way to have this problem, you first pick this algebra, you write a formula like this, pick these observables here, and then you try to first of all, you want to construct this homomorphism that exponentiates by the time that's usually too hard, and this you can construct the ground space perhaps.
Usually, I'm just confused. On the lattice, don't we need to choose a Hilbert space? Also,
Sorry?
don't we need to choose a Hilbert space?
But not to find ground space. You can say everything without going to Hilbert space. But then in a second, I'll also say how to use the big Hilbert space. So ground state is just some. First of all, what's a state? Okay.
So sorry, Anton, the HJ is in AJ. It's in the operator at a particular site rather than
HJ is an honest observable. In fact, it's usually
no. HJ is in curly script A subscript J rather than HQ. HQ was everything, right? And AJ is local. Is that the whole point of this statement?
so okay. So maybe we should do it like this. So so a set of nice local observables, like just without the closure.
I think I'm asking something else. That this expression for the Hamiltonian as the sum of commutators,
Yeah.
that's where locality is going in.
Yeah, locality is saying that how bad or good this little h of j's are, right? So each h of j just could use typically actually finite range interaction. So it actually sits not even in the closure, but actually in the actual local observables. So each j could be sitting on side j and be one everywhere some ball radius r around some j, right? So typically aj is give a product of two spins or something, and so it has usually finite range.
And why the commutator there? That's
Because you want this.
H acts on the observable. So that's the time evolution of the observable.
So the point is that H, big H, is a linear map from observables to themselves, which satisfies that. And the easiest way to construct such a thing is just take commutator with some other observable. Those are nice derivations, but those turn to be useless because it They just evolve you near the point where that observable lives.
Very good.
But you want to evolve everywhere, so you take the infinite sum.
How broad is the class of systems this is intended to apply to? So I think you said spin systems.
Well, I mean,
So it would not apply to scalar field theory, or would it?
no, it's not going to apply to scalar field theory because for scalar field theory it's very difficult to define. Well, it's easy to write down some like this, but I need to say, well, can I like exponentiate to a natural time evolution?
Yeah.
And for spin systems, you can show that for a huge, large class of these choices, there's no problem exponentiating. So there's something called the Robinson bound, which basically explains why this is so. And in general, it's very, very difficult to say for scalars. That's why fermions or spins are better. Anyway, so the point is that, well, a state, you can say what the state is. Well, just say it's some.
I don't understand the statement. I mean, couldn't you just take just a normal particle on a line at each side, lattice side? It's not well defined. Why not?
Do you want to have continuum?
There's an infinite loop as
Wait,
well.
I mean, you want each of these guys to be.
What's wrong with an infinite Hilbert space at every lattice side?
First of all, you can take observables and some, not just for spins, the observables for particular spins are just matrices, right? If you want to do, say, particle on a line, do you want to take bounding operators or bounding operators on a line, on functions on a line?
I mean, it's an infinite Hilbert space, but what's wrong?
Not Hilbert space, not called observables.
Okay, okay.
So you need to multiply observables. So, okay, you can work with that, perhaps. What I'm saying is that
You have canonical coordinate, canonical momenta. There's an algebra
you
between.
can still form this thing.
Yeah.
The question is, what to do next? Can you show that some nice Hamiltonian exponential to actual time evolution? That's hard. So, not much you can do. You can do something, but not very much. Anyway, that's why we're going to system. So here. So that's what it means to have a state, just a positive expectation value. And then you would say that it's a ground state. For some derivation H, you have this.
What is A star?
Well, it's a star algorithm for dagger. There's an algorithm dagger for this guys. It's a star and C-star algorithm. For every element is notional adjoint.
Omega is your ground state.
Yes, omega. So initial. So you have a state. This is any positive linear function, and it's called ground state. For H, you have that. Then you can simply define notion of a gap ground state without ever mentioning Hilbert space.
In the usual language, this map omega is just a
Yeah, in usual
range of A star A.
And usual language just means this. If there's some way to attach an operator to an observable, it just means this.
No, I meant the definition of psi. Sorry, the definition of psi. What is this positive function? Is it the
It's
vev,
expectation value.
the vev of A star A inside the state?
Yeah. Yes. Yeah.
Just
So
Why do you anticipate there's just one ground state?
I didn't say there's one.
I know you didn't, but
You can find any. As many as you know.
there are many
There
different
are many
states, all of
different
which
states.
are
And
ground
we discovered that we can discover this spontaneous symmetry breaking by discovering that some the states are not invariant under the symmetries of this setup. For example, we can have some symmetry of algebra in evolution, and then look for ground states. You're like, wait a second, none of the ground states I find are invariant under symmetry. So that this way we discover this spontaneous symmetry breaking of the problem. So
if we used a more traditional Hilbert space perspective, there may be many excited states which also obey this property.
this is essentially ground state.
Why?
No, it's actually on the just No, this is an exact translation from this is translation of this condition from Hilbert space.
Are you assuming that the ground state energy is zero?
The ground state energy is zero here by definition.
Okay.
I mean, what this condition says is if you act on A on the ground state, energy goes up.
Yes, is what it says. Yeah.
So it's sort of saying there are no local
Yeah.
citation.
Right. All this A's do, they create some local citation.
And where is the infinite volume limit in all of this?
Here. This was the infinite lattice to begin with. There's no
And
limit.
that's used in the rest of these formulas?
Yeah.
Where?
And definition of little A. It's not of that completed thing.
So this wouldn't, this stuff would not go through with the lattice was finite?
Well, I mean, it doesn't. This formalism doesn't buy anything new if you just have a finite lattice. In that case, you can just work with the usual formalism. Doesn't give you anything new. But then you won't discover anything like spontaneous symmetry breaking.
Yeah, that's why I'm asking.
Only the limit. So this advantage of this can work infinite volume from the start, and
So why is this better than taking the infinite volume? Sounds like.
well, okay. So one advantage is that certain things only happen in infinite volume, strictly speaking, infinite volume. So for example, when you discuss spontaneous symmetry breaking, and by taking the limit, you have to break symmetry somewhere. Right? It's pretty subtle. You have to like impose some symmetry breaking boundary condition, and take the limit. Here you have symmetry all the way through, so that's convenient. So you,
Just at some point, you'll still have to specify boundary conditions. We know that.
here you don't need to specify boundary. Just look for all like different boundary conditions would lead to this different infinite volume state.
Yeah. Which kind of don't talk to each other.
Yeah. Here they already don't talk to each other.
Well, they don't talk to each other because it's infinite volume.
Infinite volume, it has an advantage. The symmetry is built in from everywhere. So that's the main advantage.
What's the condition for it to be a pure state?
Sorry?
Is there a condition for it to be a pure state only?
Yeah, well, the of course, we're looking for pure states also.
Because you said that if you had spontaneous symmetry breaking, you would find no symmetric ground states, but there would be mixed. I mean, you could.
Well, this condition makes sense whether you know the omega is pure or not. But you can also say pure in terms of this. You define pure in this way. Pure is a state which can only represent as a leading combination of two other states. Pure means not mixed.
What's the advantage of doing this rather than having a density matrix and taking a trace?
Well, the advantage is I never mentioned Hilbert space yet. So Hilbert space you can get from
Is that an
The
advantage?
trace doesn't. The density matrix also doesn't need a Hilbert space. It's an operator, and
Hilbert space.
it does not. It's another operator. You just need a trace on the operator.
Again, that's the matrix of the Hilbert space notion. No, it's not necessarily an operator.
A question.
Oh, it's an operator, so it's all an operator, it's unobservable. It's yes.
So that's the equation omega A is equal to the expectation value for A with O, and then in the bottom there's the equation omega A star.
There's some omega missing in the top formula.
There's omega missing.
It's the state omega, so you don't want to evaluate it in the vacuum. You want to evaluate it in the state omega.
Well, that's, I guess I meant. So, there's no other state here than omega. There's some state called, there's a Hilbert space, and there's some statement called vacuum, but the vacuum represents this thing. It's just called vacuum because it's ground state. I think it was a ground state.
Let me just ask, did you want to take a break between, or do you want to go?
I think everybody's going to benefit from breaks.
So let's take, how long do you want, 5 or 10 minutes? What?
10 minutes?
10 minutes. 10 minutes break.
It's not in the algebra.
Okay. That's my hope. We went 15 minutes. You can give you some extra time.
Yeah, it'd be useful to just kind of set forward and transfer through.
Hi, this is from the last one. The definition of the ground state. Why was it greater than why was that?
Yes.
Why was that the definition of the ground state?
Why is it the ground state?
Yeah.
Well, I think it's clearer from this one. So you should say that at this stage, I could have also introduced the Hilbert space, and so it turns out that once you have any state, you can also define some Hilbert state and some way to assign an operator to every observable in this Hilbert space. So it's called Jeanette's construction. You start with an algebra and some state, doesn't matter which one. You can attach a Hilbert space. This one called H. It's bad. We have used H for Hamiltonian. And some vacuum vector to hold 0. And then some way to map an observable to operator. And in such a way that you can say that omega A is the same expectation value. So, so I will use this notation including these hats here. So the point is that yeah, in such a way that you have time evolution. Then your time evolution preserves the state, which means that you can attach you can define a Hamiltonian such that Hamiltonian annihilates the vacuum. So as a result, the condition here means that, well, since H annihilates the vacuum is the same as this. So which means the expectation value of H hat in any state created by any observable from the vacuum is positive. So that means that there are no states with energies smaller than 0. So that's what means ground state. It means that if you act on your vacuum vectors or vacuum vector by any observable, you're going to get something which has energy at least as big as the ground state, as your vacuum vector. So. Now, kind of interesting that, okay, so H hat, by the way, is a kind of weird thing. It's what's called unbounded operator. So, more generally, so any continuous symmetry, continuous. continuous symmetry of operator algebra, and the state gives you some way to define an operator in Hilbert space called the charge of that symmetry. And by the way, this way of doing things doesn't even require, this so-called symmetry to come into the Hamiltonian time evolution. So, for example, in this, similar things happen in component field theory, so except module all these UV problems. So, for example, when I say that the algebra of these densities is that, what do I mean by this row of x and row of f? For sure, they're not symmetries of the full problem because I haven't gauged anything yet. So if I just take charge density, it doesn't come into the Hamiltonian. If you smear it with some f, it's not going to come in. So these are not generators of symmetry in the usual sense. But there are symmetries at least of the also on the kinematical level. So there is a symmetries of just the algebra of variables. And the claim is somehow that you can try to define operators corresponding to them, and it's these operators which have this issue. So if you just think of them as a generator on the algebra, actually there's no such central extension. So the point is that, well, if you take commutator of this guy with an observable, you'll get 0, right? Because it's a central term. So if you just think of this, so strict actually put an operator. So if you just think about the corresponding derivation on the algebra of variables, they all commute. It's just that attempt to interpret them as operators on Hilbert spaces leads to this extension. That's kind of important.
So what does it mean that it's a symmetry on the algebra?
Yeah, it just means that it acts with the algebra. It doesn't commute with anything, right? So it's not the symmetry of a state, it doesn't commute with time evolution. It just means some kinematic thing which acts on the observables. So the only constraint from this row of x is that it's, of course, there's lots of choices for it actually. And the only constraint is that the integral of row of x over all space is your actual symmetry. It's called the Q. But the row of x is wildly ambiguous. The claim is that if you try to define them, and as far as kinematic symmetries, you can make perfect sense of them, there's no central extension there. The question is, can you define some operator corresponding to it? And that's not very obvious because you can't, because not every kinematic symmetry actually becomes an operator. So for example, lattice systems, you need to have this very important condition that you actually have preserved the state. If you don't preserve the state, then this corresponding kinetic symmetry doesn't have any operator corresponding to it. It doesn't have spontaneous symmetry breaking. You have some kinematic symmetry which comes to the Hamiltonian. But if your state is not preserved by that symmetry, there's no operator which corresponds to broken symmetries. So okay, so here's a setup as gamma system, and let us assume there's some U1 symmetry just like there. And I want to see the emergence of some deformed algebra of charges, and I'm going to continue working on this level of C-star algebra. Actually, I'm not going to even use operators in Hilbert space. So that's yes.
Sorry. So when you have a charge density occurrence, you have improvement terms.
How about?
Improvement terms without spoiling without changing them.
Yeah, these are basically the ambiguity I'm talking about is this improvement terms.
Okay.
So the claim here is that it doesn't matter how you improve, you're still going to get the central term once you define operator, and moreover, it's also the same. It's going to be the same no matter what. So that's another non-trivial statement. So let me now try to gauge a symmetry of a lattice system. So I'm assuming that there is some algebra, there is some state, and I'm not going to specify time evolution because I don't really care too much, but I'm going to specify some symmetry. that means you have some, basically have some charge. And by charge, I mean a nice derivation, and typically this derivation is just written in terms of the infinite sum of local things. So Qj is just an observable which is on some particular site. And when I say symmetry, it means the following, that, well, I already defined how it acts on observables, it's a derivation, and also want to say that this is true for observable. Now, there's some technical issues here, which are kind of important, actually. Put in quotes, because I already mentioned that, well, okay, so probably know that unbounded operator on the Hilbert space is actually not defined everywhere. It's defined in some nice values, but not everywhere. But similarly, these derivations you get, which is interesting, they're not defined everywhere in this algebra. But they're defined in some dense subspace. What's called almost local relatively, with some almost local guy, which is here, and can define Q, so it acts just on this, but you don't extend it to the bigger all observables. But it's okay, because typically physics don't about arbitrary local observables anyway. So typically speaking, even though observables with the very rapidly decaying tails, so say exponentially or something like that, almost local. So yeah, let's put this setup, and now we're supposed to extract something from this data, which perhaps corresponds to an anomaly of the theory on the boundary of this gap system.
Question? Why do you want QA to be 0 for any A instead of just the QH is 0?
Instead of what?
QH is 0. H is the Hamiltonian.
Well, I mean, this is the bulk,
and
I want the ground state not to break symmetry. So that means this. Another way to say it is that it's actually equivalent to saying that if I sort of exponentiate Q, right, of this automorphism, then it's just, so this is basically exponential.
Can you write a little bit bigger?
So,
you are writing omega of QA is 0. I thought you said with QA equal to 0 for A.
it just means that or more detail.
But there's no Hamiltonian, so there's no sense in which this is the state. It's
There's
just a state.
somewhere floating, but I don't care where it is. And for them, I'm going to assume that it's a gap Hamiltonian, so there's a gap in the spectrum.
So you do want omega to be the ground state with respect to some Hamiltonian.
Yeah, but I don't care what it is. Just want it to be nice enough. So now I want to detect something about the anomaly on the edge. And how do I do that? Well, just like on the edge, we're trying to gauge things. Here also want to try to gauge who is the symmetry. What does it mean to gauge the symmetry? Well, I would like to define a notion of density, a charge density first of all, and that notion of density is a Qj. So density of Qj is Qj. But of course, Qj is not a symmetry of the state in general, so it's not true. So problem. Not true only. So it's like gauge transformation, generative gauge transformation of a particular size. Now, here what happens is the following. So I'm going to say that symmetries of the edge field theory are the symmetries of the bulk state. So I want to preserve the state. It's going to preserve the bulk state, and then I'm going to interpret that as a statement that there's some kinematic symmetry on the bulk. So the next step is okay, that's not true. But however, as I mentioned, there's a lot of ambiguity in how we define QJs. So maybe I can improve this Qj somehow, so that to make sure that this is 0. Now, so well, I want to improve so that still it's true. So I want to say that I'll write some formula like this for different terms of Q tilde J. And I want to and I want this thing to be local and satisfy and also satisfy this. Now, turns out it's possible, and it's highly non-trivial fact. It's possible precisely. It's possible if the system is gapped. If this omega is a gapped ground state of some Hamiltonian. I don't care which one must be gapped and local, strictly local, but I don't care what it is. And one can describe ambiguity. So Q tilde J is actually something like this. There's some choice of infinite set of observables like this, where these k's are as the following properties. So that after the sum of all j's, this can drops out. Approximately localized on both I and j. And if something is localized on I and j, and if I and j are far from each other, that means actually 0. So, in other words, this actually means that k of j decays very, very fast when I and j are far from each other.
This depends on A, or it's for every A? This KIG depends on A, or this
depends on
A? You require that?
No, just modify once and for all, and then this is holds true. That's the equation.
But these two properties are not enough for that to hold true, is it? For omega of Q tilde.
No, just the claim you can find such k so that
with these properties.
Yeah. So this property just ensure that this first of all this form is well defined, because it's infinite sum is actually converted, and that's the second property. The first property ensures that this holds true, because this sum of these extras drop out after sum over all j's.
But don't you worry?
Assumption. I mean, you could have like trilocal terms with double sum of k, I, j, k.
So it's
some kind of approximate. It's just like bilocal objects. You could have trilocal.
The claim is, first of all, this is the most general way you can modify the tilde j to ensure that this holds.
Yeah, why can't you write double sum?
Well, you can, but you can only write it in this form. Claim that the most general modification of this is like adding a total derivative. So continue. You can redefine rho by divergence, and that does change the charge.
Drops out, but there's some kind of locality condition built in this, the fact that it decays.
Yeah, well,
there's only two indices and it decays.
So for this sum to even make sense, you need to put it to decay. So the claim is that the most general, you're going to prove actually that any Q tilde j, which gives you the same derivation as the original ones, must differ from in this way. Of course, this also I knew that I'll define this k for a given. So here, by the way, you see some emergence of high symmetry in some sense. actually, what is high group symmetry? Well, normally a group is just a set with the operations which what is an inverse and there's associativity. Now, high group is when you have a set with some operations. There's an inverse, but it's ambiguous, and there is a composition rule which is also ambiguous. And then associativity actually doesn't hold. If you compose elements in your chosen way, associativity does not hold, but there is some notion of equivalence between two sides of the associator equation. So there is a if you think about your group elements as transformations, then the associativity holds up to some higher transformations. And then there is some higher compatibility conditions on these higher transformations. And then, so for transformation of transformations. And then there are compatibility for those, but also transformation of transformations. So similarly here, you have these are symmetries, and but there are objects here which can tell you how to sort of do equivalent symmetries. If this symmetry is equivalent to that one, module this. This tells you how to transform from one symmetry to another. But then transformation itself is ambiguous too. You can replace this by something like this. So there's transformation for transformation, and so forth and so on. This is symmetric in 3. So on lattice, there are always higher objects besides zero densities, and that already sort of hints of a higher group symmetry.
These are like improvement terms in the continuum? These are improvements in the continuum?
Yeah, they're basically improvements, but I'm just saying that you also
in the continuum there are finitely many, I would say.
Yeah, in continuum is dimension which kind of limits you. Here you go through all the infinity principle, but in some sense, once you go above dimension of lattice, they're kind of unimportant. So in some sense, it's more complicated, but in reality, it's not really different from here.
Question?
Yes.
For a free Fermat system, is this kind of like trying to find Vanier orbitals sometimes?
I'm not looking for particular bases in the Fermat space or anything. So we're just looking for. Well, there's an analogous question for Hamiltonians. Like, say you have a Hamiltonian, you can look for unfrustrated version of Hamiltonian, but each term does not excite your ground state. That's analogous to that. There's an analogy to the charge.
Is there an algebra of extended observables on which this higher charges act? Or?
I'm going to maybe mention how you define generators associated with high observables. I'll get to that in a second.
So, Anton, maybe I'll ask another question. Suppose you're not on an infinite lattice, but on a torus, then can you always find? Then you probably cannot always find.
I don't think it matters for this. But you don't think about this, I don't know this.
Is there a proof that it's possible to satisfy that, to find K such that this,
yes,
that this charge density basically acts trivially in the ground?
Yes, you can do it for get ground states.
So is this some exact symmetry or there's some error?
No, there's no error. You can always do that.
Of
course, the difference is that these guys are not like Q's typically like sitting on a particle side. Q tildes have some tails, but they're rapidly decaying tails.
If I require no error, I guess I will have to have some tails.
Yeah, you gotta have tails. But that doesn't bother us. What's more bothersome is that even though the original Q is all commuted, because they're like defined separate sides typically, this new Q tilde don't commute. So this is not zero, but you can, okay, so another thing you can choose, it does not necessary, but it's typically possible to do. You can also choose each charge density to be itself Q invariant. Oh, let me just not write it this way, sorry. Typically, we want charge density to itself be U1 invariant, and we can do that. So, but now we can ask, okay, how about charge density at different points? Do they commute or not? And in general, there's no way to make this work. They don't commute.
But original Qs did commute or not?
Yeah.
They did.
Yeah, but here there's something defective which general cannot remove. They do not commute.
This lack of commutation is probably related to Max's question about binary states.
About what?
In the single particle context, I think finding Qs that commute is equivalent
Right,
to finding orthogonal. This is like orthogonality condition. So the Q, in his first construction, he's found some states, but they're not necessarily orthogonal. This is orthogonal.
That's right, yeah. When you have non-zero Hall conductance, but this Q tilde is never commute. So, well, turns out in general, you have this kind of relation. You can also guarantee that there is some guy now with 3 indices, Coriolis symmetric. Approximately localized.
It's Phyllis symmetric?
Sorry?
It's unsymmetric in all 3?
In all 3. So that, you know, after you sum, say, over I, you're going to get 0 or over j, so that ensuring that this holds. And it's rapidly decaying because of this. You can also guarantee that it exists. In fact, you can actually make sure that it's U1 invariant. So, okay, so now we want to connect that somehow to the Schwinger term. So here, the anomaly, if you wish, it's a, well, it's an operator thing. It's kind of a contact term because this thing's, yeah, these things rapidly decay when I and j are apart from each other, but it's not literally a contact term. So,
can it be interpreted like smeared thing? No.
Well, basically, yes, you have smearing. But let me just actually say, first of all, in what sense it's an extension about Hall conductance, right? So, but the analogy here is the following. Right here. Let us continue. So, object with a single index, it's like a D-form. So I like to think about charge density as a D-form because I can integrate it over the whole space without using metric and get an operator. So object with 2 indices like that K guy. It's a called current. So why is it current? Well, because conservation equation. People usually write this with divergence. If you think of it as a, it's better to write it without using any metric. Then you can write it this way. If rho is d-form, then j must be d-1 form, so that the exterior derivative is a d-form. So also, in other words, for current, the natural thing to compute is the integral of a flux over current through a surface. Surface has got dimension 1, so d-1 dimensional guy, so we integrate d-1 form. So currents are d-1 forms. And so forth. So this guy with 3 indices is like d-2 form. See, it's a 2-dimensional system, just a function. And now, well, analog of the exterior derivative is a summation procedure. So exterior derivative. Well, decreases degree of form. And here, how do you go from here to there? Well, just sum over 1 index. So, and even the square of this procedure gives you 0 because if you sum over 2 indices, because of skew symmetry, you get 0. So this is like an analogous is now to keep in mind. And then once you know that, you can integrate forms over things, and so over some manifolds. So how do you integrate? What do you integrate your creatures with lots of indices on the lattice? Well, for chart it's clear. So say integral of rho of x f of x would be simply sum of j q of j. So analog of this case function is the function lattice size. So here we integrate of a charge or a dimension. Sorry, what? Maybe we should do this. So integrating charge, well, a charge is given as 1 form. So integrate wedges with 1 form, then integrate. So what's analog with that? Well, here you do something like this. You get the J in some object with 2 indices. So it's symmetric. And by the way, they look very similar. So here, these guys look very similar to these ones. Also skew symmetric, but they're different because this guy has to decay when I and J are far from each other. This one doesn't. So they kind of dual to each other. So, okay, so
what is alpha here? Where does alpha live then?
So alpha, if you wish, well, the simplest case of alpha would be like if you integrate, say, full in 2 dimensions. Well, actually, it falls in d dimensions, but when integrate the here we use alpha to be a delta function supported in some 4-dimension 1 surface. Right? So in that, if you want to do something similar to lattice, you just choose again the surface, and then choose alpha, which is let's say 0 for all points. Whenever it's on 0 only when I is on one side of the surface and j is on the other side. Okay, and in those cases it's equal to 1 or minus 1 depending on whether it's choose orientation, say A and B regions. A and B. And say that alpha I j is non-zero and only when I and j lie on different sides of the surface, and then it's either 1 or minus 1 depending on whether it's I is in A, j is in B, or the other way around. But you also have the general choice of alpha is like a smearing your surface. It's similar here. If alpha is not a delta function, delta form, then you get the smear.
F is the constant function. It looks like the integration is the same as the exterior derivative.
So
your exterior derivative and your integration seem to be the same. You just sum over j if f is the constant function.
Well, strictly speaking, you cannot do it for constant. There is some constraint here because it depends on the integration. So it's kind of different for object with only 1 index because when you sum, when f doesn't have complex support, this is not really well defined in the sense of observable, but it's still well defined derivation. So yeah, in that case, it's just like exterior derivative.
Just to make sure. Then when you wrote down detect, do you mean if you find a k such that this condition is satisfied, then that k can be interpreted as the current?
No, I just meant that this k is not a current.
But I can take k to be 0 then.
It's kind of object. It's similar to a current. Well, I'm saying that a current is also the guy with 2 indices.
If I take k to be 0, I mean, in my physical system, there is some current.
Yeah, but it's not k. Current is also a guy with 2 indices with all the same properties, but it's not what you use to improve Q. It's a different. It's only belongs to the same class of object as current, the usual physical current belongs. It's not the same guy.
What's the lattice analog of the interior derivative, interior product?
Yeah, well, it's kind of this interior contraction of one with the other, so you can define it too. I don't need it though. So anyway, so the point is that let's try to massage this algebra to something called the Schrödinger term. So if you contract, if called Q of f. So you're going to rewrite it in the following form. So I'm used to symmetry here. Now, it still doesn't look like a Schwinger term because this is not central in any sense. It's just some complicated observable. But now, okay, slow down to dimensions. 2 dimensions, you're supposed to think about the one-dimensional edge. So you can imagine this, where is our edge? Our system is infinite. Well, you can say, well, the edge is infinity. It's a circle of infinity. Then it's natural to choose that F and G depend only on the polar angle.
Couldn't you just put boundary somewhere, finite distance and
I could,
infinite
but it's trickier. Yeah, so, by the way, this part of the, so this part of the, what I will talk is based on some unpublished work with Sopenko and my former students. And we actually tried that too, in the actual physical boundary. But there is trickier, not lots of things you can, well, it's tricky because many of the statements that I made before, they actually are not valid when you have a boundary because you have a gapless system. So, and why do you have a gapless system? Well, because whenever this, okay, so I forgot to say that, why this way to open conductance? Well, you can, turns out that if you sort of think the following thing, if you take the 3 regions in this, or in your lattice of this form and do the following thing. Well, this is a bunch of numbers. For each level JK, just a number because the expectation value in your state. And the same as they're called before for origin. It's a number, but this number decays very rapidly when L and J are far from each other. So if you L is say in here, J is in here, and P is there, the only it means that really only the points near this triple point contribute substantially. So it's a convergent sum, and then turns over property to the whole conductor. So this is. So and interestingly, it doesn't depend on how you choose these regions. You can vary them anywhere you like. You can choose them in different places so that you get the same number. So now we expect that number here, this number, to be the level of the Kac-Moody alpha. So how do we see that? Well, let's try to choose this f and g which depend on the polar angle. Now let's for that case, this expression here is a somewhat well-defined observable. It takes some work, but we can show that in this case it is. Now here we So I said that there is a way to attach an operator in a Hilbert space to every sort of kinematical symmetry which preserves the state. So these Q's, sorry, Q tildes. Q tildes don't excite the ground state. Therefore, they're symmetries. They're just for some operators. This operator is unbounded, but it's okay. So now this guy also corresponds to some. Okay, so Q tilde of F corresponds to some operator called QF of F, which is actually an operator on the Hilbert space. And moreover, it also annihilates the vacuum we call our vacuum. Now, so this is also true for Q tilde J, it's also true for this guy. But this guy is was another way to attach an operator to this guy, because this guy is also a local operator. So to any local operator, you can also attach an observable, an operator. But the local observable can attach an operator. So this guy is responsible to also to an operator. Now, that operator actually does not annihilate the vacuum. Because indeed, if you just take the average, you're going to get this whole thing.
So how is it possible?
Sorry?
How is it possible? It's
There are two different ways to attach operators. The first one, we can attach an operator to every local or quasi-local observable. And that, of course, doesn't have to annihilate the vacuum. It doesn't have to have zero average. There's another way to attach an operator, general unbounded, by first exponentiating to not flow. It all works for the case when you're observable, so when you can interpret. When you have any derivation, which is not excited around, you can also attach an operator, a general unbounded one. And then here we can continue. For here, these guys can only do it in one way, because they're not observable, they're just some symmetry derivations. But for this guy, there are two ways to do it. And one way is different from the other, precisely by identity times this expectation bit. So now here is a, so we can write also this following statement. Q tilde F, Q tilde G. If you do it on the level of derivations, you can just put a hat over this whole thing. There's no like extension or anything, nothing funny happening. But I can also write it this way. I can write it as average of this M MH, so plus the operator corresponding to the observable. I can call pi. So, no, sorry. What details? Same thing. So, the minus sign here. The claim is that the operator that you get by just saying, well, it preserves the ground state, therefore it must give rise to an operator, is not the same as simply saying, well, it's an observable, therefore it gets a calculation operator. The different precise expectation rate. Because one way is the now is the vacuum, the other one doesn't. And now I have all this junk here, but remarkably this part is the right thing. That is, you can show, one can show that this actually is, for S which depends on the polar angle, it's exactly equal to Hall conductance times this. So it's the same, a cycle.
So is it clear from this perspective why there are entire derivatives?
Sorry, what?
Why there are entire derivatives, d theta to the 3?
Why they are?
No higher derivatives in your...
Yeah, it's not a real statement. It's a computation. It's not very obvious. You cannot just deduce it from general properties. So And now, well, this jump can be treated of simply saying, well, I'm going to look at all these guys are some unbounded operators which annihilate the grounds, which act nicely in some way. And then among all these operators are also just normal bounded operators. So just factor by those, this is going to disappear in the code. So what is the meaning of that? Well, I'm trying to locate symmetries of the edge QFT somewhere inside the bulk. QFT lives at infinity. So acting by a local observable, quite a local observable, doesn't change it, whatever happens in infinity. So I'm taking all symmetries of my bulk, and I factor by symmetries which act inside the bulk, that don't touch the bulk. So this is some Lie algebra of symmetries infinity. Then I'm asking, is my U1 symmetry, gauge U1 symmetry, how does it embed into that algebra? And it doesn't embed in the obvious way. It embeds with the central term. The central term is the usual Schwinger term.
Well, two comments. One is we are almost near the time, but I had a question also. Is it clear that this whole conductance does not depend on how you choose your case?
Yeah, check that doesn't.
So it's universal.
Yeah. So now I don't know how to, yeah.
Could you just explain what makes the stuff in the first term different from the stuff that's in the jump? Because like,
well, I'm just saying that I'm not sure it's an artificial construction. So I just want to say that any symmetry which just comes from the combinator of the local observable doesn't act in infinity, so I'm going to neglect that. That's intuitive justification. So observables like Q till you have that, they act everywhere, including the infinity. But this guy only acts inside in the period, so I'm going to neglect those. Okay. So after I neglect them, I get the right algebra. And now I can do the same thing in higher dimensions.
Sorry, is the logic that the symmetry in the bulk is gauged?
Yeah, I'm trying to gauge symmetry in the bulk.
Mm-hmm.
And get some complicated algebra, not unclosed algebra, because this guy, has some extra stuff. After factor by the local observable, I get a closed algebra.
Mm-hmm.
It's precisely what's called the algebra. In higher dimensions, something similar works, but there you don't get a closed algebra just with charges. So if you compute, say it equals 3, you compute these guys, and after factoring, you get something which you cannot get rid of simply by saying, well, it's junk. But you get something which is some two-form symmetry. So the charge of a two-form symmetry is an object kind of like here. So let's call it M. And contracted somehow with basically GF, which is G, roughly speaking. Some lattice analog of that. And then you can ask, okay, what about two-form? So when I'm trying to gauge this guy's zero-form symmetry, I end up also with two-form symmetry. And now I can say, okay, I cannot maybe gauge just zero-form symmetry, I need also take into account two-form symmetry. And then I ask, okay, how does it commute with somehow also three-dimensional in some two-form here. And the claim is that whenever you have a non-trivial analog of all conductance in 3+1, well, this case, so this is equals 4. So this is equals 4. The edge is three-dimensional, not the bulk. So when you do it for like this, then you'll find that actually the result is again a local observable plus a central term. So you get, and you get in this case f, which is alpha 2 plus jump, which is local observable. So this is a bit like this Fadeev-Shatashvili algebra, in the sense that you have some higher form symmetry analogous to the A that has gauge field, except there's no gauge field anymore, it comes from the lattice. So the level here is that your four-dimensional conductance. So you can sort of see all these structures emerging from just from the pulp, and hopefully one can not just define that structure to the algebra, but also be able to act actual computer space with a boundary conflict or something like that. But I don't know how to define that. So,
We're a bit over time again. A couple of urgent questions.
Hey, can you do a construction like this for the thermal Hall connectivity?
no.
I was wondering if you have made a connection with some other works going from the planetarium community, which generated some interest in recent years about their motivating question was, suppose someone gives you a 2D wave function, what correlation function extracts the Carnot-Sandel charge? And they also have these kind of tripartitions, and I'm wondering, like, it seems like it might be a nice link for that.
Well, I think both that work in Canada and our work is inspired by the same appendix D digitized paper. That's the reason why I see the same pictures. So, but in my opinion, there's no way to extract self-control charge directly from the wave function. So I'm not convinced by the argument in this paper.
Okay.
It's true, it works for free systems. Okay. It doesn't prove that it works for free permanent systems, but for interactive systems, I don't know why it shouldn't work.
But I mean, if you had a constructive approach to K, this would give it, or if you would.
That doesn't work for energy, so there's no. This is for you once, and okay, I don't do have to do something to do with Hamiltonian rather than charge. So there's no known way to extract thermal conductance from the wave function in general.
Could you explain why the theory being gapped was important for finding the Q-utilities, or what really goes wrong if you don't?
Well, that will take some time.
Okay.
It's non-trivial.
I think, can we stop here because we need to take a photo and we need to go get lunch. There's a large break. Today we start at 3, right? Is that correct? I think Luca. Okay, so we'll reconvene at 3. Thanks, the speaker.